In this video, we solve problem 15.2.014 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to consider the following. C is a path. It consists of line segments that start at x equals 0, y equals 1, and go to 0, 4. And then from 0, 4, you go to the point x equals 3, y equals 3. In part A, we're asked to find a parameterization of the path C, and in part B, we're asked to evaluate this line integral of the scalar function over the path C. Now, there are actually infinitely many ways to parameterize that path, but WebAssign has presented us with this much. And when they present us with this much, there's really only one answer that can go in this box. I'm going to just focus on answering the question first, and then it turns out the way that I tend to solve it anyway, I would end up with a parameterization that looks like this. But we can talk about the fact that there are different parameterizations and how we might get different parameterizations through looking at the parameterization differently. So let's start by trying to come up with that parameterization. If we want to find a parameterization, the first thing we always ought to do is sketch the path. So they say start at x equals 0, y equals 1, and go to x equals 0, y equals 4. That's the first part of C. And then they say from x equals 0, y equals 4, go to x equals 3, y equals 3. And that's the second part of C. Now, if you want to, you can say, well, this is clearly piecewise smooth. That's one smooth piece, and that's one smooth piece. You can label this first part of the path C as C1, and the second part of the path C as C2. And we'll think of C as the union of C1 and C2. Generally, orientation matters, so we want to put arrows on there that indicate we're going this way, and then we're going this way. And then the question becomes, well, how do I parameterize that? Well, you just look at one piece at a time. So let's look at C1. I will say that that is parameterized by the vector valued function R1 of t with components x of t and y of t. If you want, you can put x1 of t and y1 of t. It's not necessary. And I want to start here at this location when t equals 0. Now, when I'm deciding what my upper limit for t should be, I'm trying to keep this as simple as possible. So one way that you can make everything as simple as possible is to imagine being a little particle traveling along this line segment. At t equals 0, I'm here. And if I'm a particle traveling along this line segment, maybe like 1 second later, I'm here, and another second later, I'm here, and a third second later, I'm here. So this would be at t equals 1, I'm here, t equals 2, I'm here, and at t equals 3, I'm here. So if I'm traveling at a rate of 1 unit change in y for every second, I might start here at t equals 0 and end up at x equals 0, y equals 4 at t equals 3. So with that in mind, I might let t go from 0 to 3. And then I say to myself, okay, when I'm looking at this line segment, what is the easiest thing to describe? Is the x very simple or is the y very simple? Well, I think the x is the simplest, because if I'm on this line segment, x is just 0. X is 0 the whole time when we're on the y-axis. So this is going to be a 0. And then the question becomes, well, what is y? What is y in terms of t? Well, y is changing. When t is equal to 0, we want y to equal 1. And when t is equal to 1, we want y to equal 2. When t is equal to 2, we want y to equal 3. When t is equal to 3, we want y to equal 4. I'm not so interested in the points in between. All we really need are 2 points. But basically what I'm doing is I'm looking for a linear relationship between t and y. I want t to go from 0 to 3. At t equals 0, we want y to equal 1. And at t equals 3, we want y to equal 4. Now, because I am imagining that y is changing at a rate of 1 unit per second, there will always be a relationship between these two columns that's relatively easy to find. Like you might add them or subtract them and get a constant number if we're using this idea of traveling at 1 unit per second. If I subtract these, 1 minus 0 is 1, 4 minus 3 is 1. So it looks like y minus t is going to be equal to 1. And if I add t to both sides, I get y equals 1 plus t. And check it out, make sure it actually works. When t equals 0, y equals 1, which is what it's supposed to be. When t equals 3, y is equal to 1 plus 3, which is 4. It's exactly what it's supposed to be. So t equals 0, y equals 1. T equals 0, y equals 3. So we have that right there. Now this is component form for r of t. You could write it in terms of standard unit vectors I hat and j hat this way. It's 0 times I hat plus 1 plus t times j hat. And of course, most of the time we don't add the 0. So we just have 1 plus t times j hat on the interval from 0 to 3. And that turns out to be exactly what they gave us here. If they didn't give that to us, this is what the parameterization I would have come up with. Okay, now let's look at the second part, C2. Now this one is a little trickier because x is changing, x is going from 0 to 3, and y is changing, y is going from 4 back down to 3. And I'll let my x and y components be called x sub 2 of t and y sub 2 of t. And I want to start at t equals 3. So I'm imagining that this is the path traveled by some little particle along our curve. And then you'd say, okay, well, you've got some options. If I want x to change by 1 unit for every 1 unit change in time, x is going from 0 to 3. So if x is changing by 3 units, I might let t change by 3 units. I might let t go from 3 to 6. Or alternatively, I could let y, or I could let t, the range for t, depend on the range for y. So I'd say, well, y is decreasing by 1 unit. So let's let t go from 3 to 4 and let the relationship between y and t be 1 unit per second. I'm going to use the range for x because that's what they used here, and also because I think I probably would have chosen the larger interval anyway. So we're going to let t go from 3 to 6 because x is changing by 3 units. And then we're going to say to ourselves, okay, when t is equal to 3, I want x to equal 0. And when t is equal to 6, I want x to equal 3. So what is the relationship between these two variables have to be? If I add these together, I get a 3 and a 9. That doesn't help me. But if I subtract them, 3 minus 0 is 3, and 6 minus 3 is 3. So it looks like t minus x is 3. So you can subtract t from both sides, multiply both sides by -1. That's going to change the order on the right-hand side. And we end up with x equals t minus 3. Now check it out, make sure it works. When t equals 3, I want my x value to be 0 because x is equal to 0 on the y-axis, right? T equals 3, x is 0, good. When t equals 6, I want my x value to be 3. 6 minus 3 is 3, so it works out. That's like a particular time. I'm at this particular location. And you might say, okay, well, how do I find the y value? Well, the y and the x are related by the geometry of the problem. X and y are related by the equation of this purple line. And that's easy enough to find. It's y equals mx plus b, and the slope is negative. We can see it. We go down 1 and over 3, so the slope is -1/3. So we have -1/3 times x plus the y-intercept, and it intersects the y-axis at 4. So no matter what x is, y has to be -1/3 of that plus 4. Since we already know what x is in terms of t, we can just substitute that in there and we'll get y in terms of t. So we have y equals -1/3 x plus 4. And remember, x is equal to t minus 3, so I'm substituting that in. Distribute the -1/3, and -1/3 times -3 is a +1. We end up with -1/3 t plus 5 for our y value. Whenever I derive an equation like that, I always like to check it just in case I've made a mistake somewhere. Let's see. When t equals 3, I want my y value to equal 4. Does that work? If t is 3, I have -1/3 of 3. So it's going to be a -1 plus 5, which is 4. Good. And when t equals 6, I want my y value to equal 3. T is 6. 1/3 of 6 is 2. This is going to be -2 plus 5, which is 3. So we're good. So those are our component functions for r sub 2 of t. You can write this instead of writing it in component form like that. You can write it in terms of standard unit vectors I hat and j hat this way. It's t minus 3 times I hat plus the quantity a -1/3 t plus 5 times j hat. And r of t is this on the interval from 0 to 3, and it's this on the interval from 3 to 6. So when we put those two pieces together, we get the answer to part A. That's our parameterization. So we had 1 plus t times j hat on the interval from 0 to 3. And then we have t minus 3 times I hat plus -1/3 t plus 5 times j hat on the interval from 3 to 6. And that is what we will write in this little answer box right here. Write this piece. Okay. Now, the second part of the question asks us to do this. It says, find the line integral over c of this scalar function, 2x plus y times, or 9 times the square root of y ds. Now remember, whenever you're evaluating a line integral, we've got a lot of variables. We want to know how, we want to add up the values of this function over this curve as we go from point to point at all the different xy pairs on that curve. We want to add all of those pieces up and multiply by a tiny length of the curve ds. In order to tie all of the variables together, we need a parameterization, and now we have it. And if I think of this piece, that first piece, as parameterizing C1, and the second piece is parameterizing C2, and then C, remember, is the union of C1 and C2. It's this piece plus this piece. This is actually just equal to the line integral over the first piece plus the line integral over the second piece. And we need a variable to tie all of these pieces together. The variable that ties everything together is t, because if I'm on this curve, x is a function of t and y is a function of t. And if x is a function of t and y is a function of t, I can write this in terms of t, and ds can be written in terms of t. And we know that t starts at 0 and goes to 3 to get from there to there, and t starts at 3 and goes to 6 to get from there to there. So t ties everything together because we've got all these different locations on the curve, x of t, y of t, that depend on t. And of course, the length, the little arc length piece, the length of the curve, that depends on t. So that's the plan. So that means we need to do a few things. We need to evaluate this in the following way. We're going to take this function, we're going to write it in terms of x of t and y of t. So we'll have 2 times x of t plus 9 times the square root of y of t. And then we'll multiply by ds, which is the magnitude of our 1 prime of t times dt. On that first piece, t goes from 0 to 3. And then we're going to do the same thing over here. T will go from 3 to 6, though, this time. We'll have 2 times our x value plus 9 times the square root of our y value times the magnitude of our 2 prime of t dt. And if you have trouble remembering that ds is actually equal to this magnitude of r prime times dt, think of this as velocity. Like if r of t represented the position of a particle along a path, r prime would be the velocity. The magnitude of the velocity is the speed. So we're saying that a tiny length is equal to speed times time. And I think we all remember that if we took some number of meters per second and we multiplied by some number of seconds, we'd get meters back. So that little physics analogy helps me to remember that length will be given by speed times time. But you just have to make sure that you're using the right position function. For the first part, we're using this position function. For the second part, we're using this position function. Okay, and then we have to substitute in x of t here and y of t here. Well, r1 of t was, they have 1 plus t times j hat, or I like to write it in component form. That's x of t equals 0 times I hat plus the quantity 1 plus t times j hat. This first component is your x of t. The second component is your y of t. So we're replacing x with 0, and we're replacing y with 1 plus t. And then we have to find the magnitude of this guy. Well, if r sub 1 is equal to this, I'm going to focus on the component form now. The derivative of 0 is 0. The derivative of 1 plus t with respect to t is 1. That is a vector that goes 1 unit in the y direction, and that's it. So clearly its magnitude is 1. Now, if you want, you could always use the formula, and you will also see that the magnitude is 1. Okay, so this is 1. Now over here, r sub 2 is equal to this. I'm going to write it in component form. So this first function is my x of t. The second function is my y of t. So this is 2 times x, which is t minus 3, plus 9 times the square root of y, which is this 5 minus 1/3 t. Or you could write negative 1/3 t plus 5, same thing. And then we have to multiply this whole integrand by the magnitude of r prime of t dt. And we're talking about the second part, so we're calling it r sub 2 prime. It's easy enough to find. Take derivative component by component. The derivative of that piece is just 1. The derivative of that piece with respect to t is just negative 1/3. And then when we find the magnitude, we take the components, we square them, we add them, and we take the square root. So this is 1 plus 1/9, or if you prefer, 9/9 plus 1/9, which is square root of 10 over the square root of 9, which is 3. So this turns out to be square root of 10 over 3. Okay, so we just got this integral to evaluate and this integral to evaluate, and that will give me the length of that curve. Let's do the first piece first. Just going to put a star by that. Okay. So we've got the integral from 0 to 3 of 2 times 0, which is 0, of course, plus 9 times the square root of t plus 1. I'll write that as t plus 1 to the 1/2. And this magnitude happened to be 1. So we've got 1 times dt there. That's easy enough to evaluate. We'll just do a u substitution. We've got a function nested inside another function. U equals t plus 1. du is the derivative of that, which is 1 times dt. So that's going to be a u to the 1/2. dt can be replaced by du. And we're going to need new bounds. These are t values. Whenever I write my integral in terms of u, I need the bounds to be u values. These need to be related to the variable over here. To find the bounds for u, all we do is substitute the bounds for t into the equation for u. So when t equals 3, u is going to equal u of 3, which is 1 plus 3, which is 4. So that's our new upper bound. And when t equals 0, u will equal 1 plus 0, which is 1. And that was our original lower bound, so this is our new lower bound. So we have the integral from 1 to 4 of 9 times u to the 1/2 du. Easy enough to evaluate. Bring the 9 down, add 1 to the exponent. Divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Evaluate from u equals 1 to u equals 4. 3 goes into 9 3 times. We end up with 6 times this u to the 3/4, or sorry, 3/2. Evaluated from u equals 1 to u equals 4. So we'll have 6 times 4 to the 3/2 minus 1 to the 3/2, which is just 1. And any number to the 3/2 is that number times the square root of that number. So we've got 4 times 2, which is 8. We have 6 times 8 minus 1, which is 7. And that's going to be 42 for the first piece, first part. Okay, so we've got to add that to the value of the second integral. Second integral was the integral from 3 to 6 of 2 times the x value on that integral, or x value on that part of the curve. X in terms of t was t minus 3. And we add 9 times the square root of the y value, and the y value on that curve was given by this. And then we multiply by ds, which is like speed times time. So we take the magnitude of the velocity, which gives us this, square root of 10 over 3, and we multiply by dt. So that's where that came from. And I would probably distribute the 2. And now we just need to evaluate this integral. I would factor out the square root of 10 over 3. Maybe do this first piece first. And then over here, take out the square root of 3 over 10 as well. Maybe factor out the 9 as well. And then we'll evaluate this piece. It's 3 to 6, not 0 to 6. Okay. So I think I will do this little piece later because it requires a u sub. But for this one, it's pretty straightforward. We'll bring the square root of 10 over 3 down. Then the antiderivative of 2t with respect to t is 2. And you add 1 to the exponent and divide by the new exponent. Antiderivative of a constant with respect to t is that constant times t. Evaluate from 3 to 6. And so we'll have the square root of 3 over 10. At 6, we get 36 minus 36. Okay. And then at t equals 3, we're going to have 3 squared, which is 9, minus 6 times 3, which is 18. So you have 0 here, and this is a negative 9. We're subtracting a negative 9. That means we're adding 9. So you end up with square root of 3 over 10 times 9, or 3 times the square root of 10, because 3 goes into 9 3 times. Just the first piece, that's what we have there. And then over here, we're going to have Well, 3 goes into 9 3 times. This is 3 times the square root of 10 times that extra piece. So there's not enough room on my paper. I will do this on another sheet of paper. So far, the original line integral is this. Oops, didn't need that to be so long. The first part was 42. That was the line integral over C1. Then we've got the other piece, which turned out to be 3 times the square root of 10. And now our last piece is 3 times the square root of 10 times the integral from 3 to 6 of 5 minus 1/3 t raised to the 1/2 power dt. Okay, so now we just want to evaluate this. Well, that requires a u substitution. I've got a function inside another function. So my u would be this. The derivative of that is just derivative of a constant, which is 0. I've got a constant times t, so you bring the constant down. And I don't actually have a negative 1/3. So I think I'll multiply both sides of this equation by -3 to get dt by itself. So this will be u to the 1/2, and dt can be replaced by -3 times du. Now remember, those are multiplying each other. I'm not subtracting 3. I'm multiplying by -3 times du. So we have the 42 and the 3 root 10, and then the 3 root 10 times this integral. I've got a u to the 1/2, and then a -3 times a du, but I do need new bounds. These are bounds for t. I need bounds for u. When this integral is written in terms of u, these numbers here have to represent u values, not t values. And it's easy enough to find the u values that go with these t values. You just plug these t values into this equation, and that's it's going to give you the corresponding u values. So I'll plug in t equals 6. And then I will substitute in t equals 3 and see what the corresponding u values would be. Well, 1/3 of 6 is 2. So this is 5 minus 2, which is 3. T equals 6 was the upper bound. So u evaluated at 6, which is 3. That's the new upper bound. T equals 3 was the lower bound. So u evaluated at 3 is the new lower bound. 1/3 of 3 is 1. 5 minus 1 is 4. And if you don't like the fact that that 3 is above that 4, you can flip it and multiply by -1. That's totally fine. We learned about that in Calculus 1. So I'll have a -3 times this 3 root 10 is going to be a -9 root 10. And if I want to change the order here, make that an integral from 3 to 4, I can, as long as I multiply by -1. And then we just use the power rule for this piece. Add 1 to the exponent, and then divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Evaluate from u equals 3 to u equals 4. 3 goes into 9 3 times. So I have 6 times the square root of 10 times 4 to the 3/2 minus 3 to the 3/2. Just factoring out the constant and just evaluating that at 4 and 3 and subtracting. Well, this is the same as 4 times the square root of 4. Square root of 4 is 2, so that's 8. This is the same as 3 times the square root of 3, which doesn't simplify much. So we've got 42 plus 3 times the square root of 10 plus 6 root 10 times 8 minus 3 root 3. All right. You might wonder if this simplifies at all. I don't really see that it simplifies, guess we could call this 48 times the square root of 10 and negative 18 times the square root of 30. But there's nothing that all three or all four of these terms really have in common. Let's see. Well, 42, 3, 48, and 18 are all divisible by 3. But factoring out a 3 really isn't going to make this much simpler. So I think I would probably just leave this as is. If you're saying to yourself, what does that number mean? Well, it's the line integral of this scalar function over the curve C, where the curve C is this curve. It's a piecewise smooth curve. Smooth on this piece, smooth on this piece. We evaluate this integral, figure out what that sum would be, and then we evaluate this integral. Or then we go from here to here. We figure out what the sum would be, and then we add those two pieces together. And that gets us this answer right here. I don't know why I didn't think of it sooner. These are like terms, so I guess we could simplify just a little bit more. And that's 51 times the square root of 10. And you've got that. And again, you could factor out a 3 if you wanted to, but it's not going to make it much simpler.